Hello. In this video, we're going to finish up the Introduction to Three Dimensions section. We're going to start off by going over the distance formula. So the distance formula in 3 dimensions is the following. First, let's actually draw a picture so that we can understand what we're talking about. Okay, so let's say we have 2 points, and we'll say point 1 is right there, and it's given by coordinates x1, y1, z1, and then we'll say point 2 is given by x2, y2, and z2. All right, so this point is x1, y1, z1. Here we have, and we'll call that p1. And here we have x2, y2, z2, and we'll call that p2. So the distance formula, so between p1 and p2, is equal to the square root x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Okay, so it looks fairly similar to the distance formula in 2 dimensions, except we have an extra component for z. Okay, so what I want to do next, before we go through and actually do an example, is I want to go through and prove the distance formula to you. This is something that it's going to be common throughout the course, where I'll stop and I'll just prove something that I've just finished stating. So let's go through and prove that this is actually is the distance formula. Okay, so the way that we're going to do the proof, let me just take this picture here and redraw it, but bigger. That will make it so that it's easy for us to go through and prove it. Okay, and let's go through and say that's our first point. Okay, and then let's say way over here so that it's easy to see, we'll have our second point. Okay, so this is x1, y1, z1. This whole distance here is x2. This distance is y2. This is z2. So the way that you go through and prove the distance formula is you go through and you use the Pythagorean theorem. All right, so to do that, what we want to do is we want to draw a line. Let me use the line drawing tool. There we go. So we're going to start off with draw that line. And then if you just take that line there and you projected it down onto the XY plane, you just flattened this picture, what you'd end up getting is you'd get this line. Okay, so this here is directly above that. Okay, now this is not a triangle, right? Which is what we would need for the Pythagorean theorem. However, we can do one more thing, and that is that if we just take this piece or this piece, if you just kind of lift the projection up until it hits this point here, what you're going to get is you're going to get the following. So you're going to get another line that's just parallel, just like that. Let's move that down a little bit. Okay, and now if you take a look at this picture, so we've got, here's one side, here's another side, and then this line, this squiggly line here is parallel to the z-axis. And what do we know about the z-axis and the xy plane? We know that it's at a 90-degree angle. So that means this is a 90-degree angle, and then this would also be a 90-degree angle. So what we've got here is we've got a right triangle, which we can go through and use the Pythagorean theorem on. So if we go through and label the sides of our right triangle, let's say this side is D. Okay, so that's the hypotenuse. And so we know with the Pythagorean theorem, we know that we have D squared equals something. Let's the D for distance, right? And then let's temporarily, we'll call this A. So it's going to be A squared, and let's call this B. So we're going to have plus B squared. All right, so we need to figure out what A and B are. Now, the easier of the two of these to find is actually going to be B. If you look at this squiggly line here, this is a straight line. I just drew it squiggly for whatever reason to go through and represent so you could clearly see where the x2 y2 z2 is, and that's directly above this point. It's a straight line. It's a straight distance, and we know what this total distance is, right? We know this total distance is z2, right? We said that's the distance up off of the xy plane. And then we know on this end that this total distance right here, right, that's the same thing is z1. And if you just shift that over, that tells us that, let's just get rid of this z2, that's kind of in the way. We know that this distance here is z1. Okay, and so what we want is we want this distance b, the side of our triangle here. And if this is z2 and this is z1, the way that you go through and find the difference between two distances is to subtract. So we can go through and we can just pop in. Let's do these one step at a time. We'll leave that for a squared for now. This is going to be z2 minus z1 squared. Okay. So that's B. All right, that's easy enough to go through and find. Now, next we need to go through and figure out what A is. And the key to figuring out what A is this line that we drew down here on the XY plane. Okay, if you think about, or if you figure out what the coordinates are, this point here, right? If you just ignore the Z1, if you just get rid of the Z1, that's X1, Y1, 0. Okay, X1, Y1, 0. I don't really have enough space here, but x1, y1, 0. And this point here is x2, y2, 0. Okay, and so if you think about going through and finding this distance, well, if both of these coordinates are 0, that's the same thing as going through and finding the distance, right, in 2 dimensions between, x1, y1, and x2, y2, isn't it? Right? So the 0 is not going to contribute any distance. These points are both flat on the xy plane. And so you could go through and just take them and just ditch the 0 coordinate. And then you have your 2 points that are on the xy plane. And we could go through and find the distance between them by using the distance formula in 2 dimensions. Right? So if this is P1 and P2, then the distance between those is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay. And so that's this distance here, and that's the same distance as A. So we know that A equals that. And then we could pop that in there, and you'll get d squared equals the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, and then that's going to give us d squared. And I forgot my square here, right? So this square right there. And then the square root and the square are going to cancel, and so you'll get x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And then finally, we just take the square root of both sides, and we get d equals the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And there's the proof. All right, so that proves that the distance between these 2 points is given by this formula. Okay, so next thing we're going to do is we'll go through and we'll practice using the formula. So let's do an example. Let's say we want to go through and find the distance between 1, 2, 3 and -1, 4, I don't know, 6. All right, so we've got our handy distance formula. We'll say this is P1 and P2, and the distance between P1 and P2 equals the square root. And if this is P2, then it's going to be x2 minus x1, so we're going to get -1 minus 1 squared, and then y2 minus y1, so we're going to have 4 minus 2 squared, and then z2 minus z1. And so if we just simplify that, this is -2 squared, so that's 4. This is 2 squared, that's also 4. 3 squared, that's 9. And we get the square root of 17. Okay, and that's the distance formula. Okay. All right. Next, moving on. The next thing we're going to look at are spheres. So first, what is a sphere? What's the technical definition? I forgot. Equidistant R from center A, B, C. Okay, so a sphere is a set of points that is the equidistant distance R from center A, B, C. Okay, so if you were to maybe draw a little picture here, if we said that the center here was at 0, 0, 0, then we want to just go through and draw all the points that are equidistant away from that. So you can do your best here, draw something like this. This is a lot easier on the paper. Something like that. That looks a little sphere-ish. All right, and the idea is that if you picked any point on the edge of the sphere, any point at all, you pick this point or this point or this point or this point down here, those points are all, if you calculated the distance between that point and the center, you'd get R, you'd get the radius. Okay, so that is what a sphere is. It's the set of points that are all distance R from the center. Okay, so the formula for a sphere is given by x minus a squared plus y minus b squared plus z minus c squared equals r squared. And you can look at that and you can say, oh, wow, that looks a lot like the sphere formula, or sorry, the circle formula, except we added another component. And that's correct. Okay, the way that you can go through and prove that this formula does meet this requirement is to take this requirement here and just plug it into the distance formula, right? So the fact that you've got this equidistant part in the definition for the sphere is the critical part of going through and proving that the formula relates to the distance formula and turns into this. Okay, so if you just go through and say, you know, let a point on the periphery here be x, y, z. So we're just going to say it's a generic. Frequently, when you represent generic things, you use x, x, y, or x, y, z in this case. So that's going to end up being this thing here. And that's when you go through and you use the sphere formula, a, b, and c are given, and you plug them in here, here, and here. And r is given, and you plug it in here. And then the point that you plug in to determine whether it's on the sphere goes here, here, and here. So that's the point that's on the edge of the sphere. And then you could say, let the center be ABC, and let the radius be R. Okay. And then again, going back to the definition says a sphere is a set of points that are equidistant from the center ABC. So if you take a point and ABC and you calculate the distance between them, you should get R. And so we could go through and use the distance formula. We'll say this point is P1, this point, hold on, let's do it the other way. No. Let's say this is P2, this is P1, and so the distance between P1 and P2 equals the square root, right? And it's going to be P2 minus P1, so we're going to get x minus A squared plus y minus B squared plus z minus C squared. And then the distance, so the distance between these 2 points should be, right, the distance between a point on the edge, x, y, z, and the center, a, b, c, is supposed to be r. So the distance is supposed to be r. And if you just pop in r for that, you get this. And then if you square both sides, and look at that, you get the sphere formula. Okay, and if you want to go through and derive the circle formula sometime, it's derived the same way, because a circle and a sphere are basically very similar objects, same object in their coordinate system, right? In their universe, right? So in a two-dimensional system, a circle, and a three-dimensional system, a sphere, they're basically the same object. Let's go through and do a couple examples with spheres. Right, so what type of thing might you be asked to do with a sphere? You might be asked to go through and find the equation of a sphere. All right, so here is an example. And so what you want to do to go through and find the equation of a sphere with radius 2 that's centered at -1, 3, -4 is to go through and just take that information and plug it into the sphere formula, right? So the sphere formula is x minus a squared, y minus b squared, and z minus c squared equals r squared. So we know that a, B, C is the center, and it told us the center is -1, 3, -4. So just pop that in there. So we're going to have x minus -1, y minus 3, and z minus -4. And the radius they told us is 2. and then just simplify. Right, so double negative, we get x plus 1, y minus 3, and z plus 4. And then 2 squared is 4. And there you go. All right, so that's how we could go through and find the equation of a sphere. And let's go through and do another one. So find the equation of a sphere centered at 1, 2, 3 that touches the point 4, 5, 6. All right, so if you were to draw yourself a picture, so we've got a point here that's the center. That is 1, 2, 3. And we've got another point out here that is 4, 5, 6. And the sphere touches that point, right? So if we were to go through and draw our sphere, you draw something like this. It doesn't look very spherical, but you get the idea. All right, so it just touches that point. Okay, so just touch that. Okay, so if we're going to go through and find the equation of this sphere, to go through and find the equation of a sphere, you need to use the sphere formula. And to do that, we need two things. We need the two things we had here. We need the center and we need the radius. So they gave us the center here, but they did not give us the radius. So what we need to know is we need to know the distance between the center and the edge. So how could we find that? Well, if they gave us this point, the center, and they give us the point that is on the outer edge, you could use the distance formula to find the distance between those two, and that would give you the distance between the center and the edge. So that's what we're going to do. All right, so go through and say we're going to find the distance here, and it'll be 4 minus 1 squared plus 5 minus 2 squared plus 6 minus 3 squared. And so that's going to give us the square root of 3 squared plus 3 squared plus 3 squared, which is the square root of 27. Okay, so we have the distance between the center and the edge, otherwise known as the radius. So the radius is the square root of 27. And now to go through and find the equation of the sphere, take the center and take the radius and just plug it into the sphere formula. So we're going to get x minus 1 squared plus y minus 2 squared plus z minus 3 squared equals the square root of 27 squared. And then we could simplify that. This is x minus 1 squared plus y minus 2 squared plus z minus 3 squared equals 27. Okay, there you go. So that concludes this second video on an introduction to three dimensions. Thank you for watching, and I'll see you next time.